In this lecture, we will be going over what is a theory. And I'm going to be talking about theory strictly in the context of psychological science and neuroscience. This lecture depends on the readings of Van Rijn and Baggio, Theory Before the Test, How to Build High Verisimilitude Explanatory Theories in Psychological Science, and Guest and Martin, How Computational Modeling Can Force Theory Building in Psychological Science. If you have not yet read these articles, please pause, read them, and come back. Today's lecture will go over two broad topics. First, I'll explore what is a theory in psychology and neuroscience. And then I'll go into detail about formulating a good theory. And what I mean by good theory is an effective theory in the context of applying data science tools to test your theory. Now, what is a theory in psychology and neuroscience? These two fields are awash in different types of theories, ranging from theories on simple behavior and cognition, theories of social dynamics, theories of development, theories of learning, stages of growth, mechanisms of neural circuitry. And all of these different types of theories really boil down to theories that sit on a range or a continuum from verbal-only theories, which are described strictly in prose form, to strictly quantitative theories that are restricted to a very specific set of equations. Now, most theories sit somewhere in the middle. There's very few pure quantitative theories and very few pure verbal theories. But this shows the range of types of theories that are used in our field in order to build predictions and explanations of behavior and neural systems. What I'd like to do is dig a little deeper to explore the fundamental form of a theory and relate it specifically to how we can apply data analytic tools to understand and test it. Because the form of your theory will define and shape the way you test it. So first we have to ask a question: what is a theory? And for this, we're going to rely on the definition and framing put forth by Van Rijn and Baggio in that reading. These authors define a theory as a description of a set of capacities. What are capacities? They're essentially a set of abilities. Any system, whether it's a little worm, a fish, a human being, an artificial intelligent agent, has a set of abilities or behaviors that it is capable of doing. And so at a principal level, for any intelligent system, we're trying to understand the capacities of that system. These become the primary explanata, or things to be explained, of the field itself. Now, there are two forms of theories, or two classes of theories, that are commonly seen in psychology and to some degree neuroscience as well. There are informal theories, which involve building a description based on a collection of observed effects. So these can be thought of as very classic psychological theories like psychodynamics. And a lot of times these theories are really ways of trying to assemble things that you've observed first and then figure out a way to explain them. And the authors make the analogy that this is like trying to write a novel by collecting sentences from randomly generated letter strings. And a lot of times if you go into trying to assemble a massive set of observations without a core mechanistic construct to guide you, what you'll end up doing is really just trying to put together random sets of associations that may or may not be causal. And the authors argue that this is a very ineffective way of trying to understand the capacities of behavior or neural systems. They instead argue that we should be focusing a little bit more on, or very much more on, formal theories, which involve constructing a description using formal logic prima facie via a constructive strategy. So the idea is apply a set of logical constraints to build a theory, a hypothesis, before looking into the world of observations in order to evaluate that theory. Now, in order to build this, you need a set of logical constraints in order to put together an effective and testable theory. So they argue that you need a set of plausibility constraints. These are constraints that are determined mostly by logic. And then you need to develop the theory through a theoretical cycle of tests and evaluation and revisions. What are plausibility constraints? They're effectively a set of assumptions. So the first assumption is that a theory must provide a means for making rigorous tests possible. In a classic sense, this is the idea of falsifiability. You can effectively only test a theory using modern scientific principles if you can formulate it in a way that it can be falsified. 2, you should restrict the number and types of theories or hypotheses being considered for testing. So you need to have the ability to channel your framing or your research to very specific effects. And really, this is a matter of acknowledging that we all have limited time and resources. So an effective theory is one that makes a strategic decision about what to test. And these plausibility constraints basically form the shape of your theory to fit within the scope of feasibility for testing it. Okay. Now, if you have these plausibility constraints in mind, you have prima facie logic that you can use to construct a theory. One major question is what do you look at? In psychological and neurosciences, we can have theories that talk about gross behavior. We can have theories that talk about synaptic plasticity. So the scope of your theory really depends on the level that you're looking at it. And the authors bring this up in the context of Marr's 3 levels of analyses. Marr's levels of analyses were proposed by David Marr in 1982. He was a computational vision scientist who said that in order to understand any intelligent system, you have to look at it from different levels and understand it from different levels. So Marr proposed 3 levels, and you can think about these as just really conceptual anchorings. So if you're going to be evaluating a system, are you looking at it at some range between these 3 levels? They're not hard categories, but more anchor points for thinking about the problem. The first is the computational level, which is essentially or effectively the goals of the system. The second is the algorithmic level, which is how the system or the set of processes that implement that goal. And then you have the implementation level, which are the core mechanistic systems that implement the processes that give rise to achieving those behavioral goals. Now that's a little opaque. You can consider this by analogy. Imagine trying to describe the flight of a bird. Now, the primary computation of flight of a bird is flight. So that is the goal that the animal needs to achieve. It achieves this through the process of flapping its wings, which you can consider the algorithm of flight in a bird. And that is implemented via a set of very specific phenotypic features on the bird, including feathers and its wings, its bone structure, its weight, its muscle tone. All of those are features that implement the process of flapping that give rise to flight. So you can understand now how the framing of your theory at different levels will give you a different understanding of the system. If you ignore the process of flight and only focus on the biomechanics of flapping, you're not going to necessarily understand how that flapping or how changes in that flapping give rise to different dynamics of flight. If you only focus on the process of the protein structure of feathers, you don't gain any intuitions necessarily of the process of flapping that gives rise to flight. So in this way, if you think about each one as being a different level of mapping between implementation to achieving a goal, you can understand and you get a more holistic understanding of the process of flight. Now, we're not studying birds necessarily, or most of us probably aren't studying birds. We're studying other animals and behavior. So let's break this down into parts more consistent for psychology and neuroscience. So in the Marr system, you can think of computation as being the behavioral goal of the system. How do you reach for a target? How do you decide which action to take? What is your motivation? What is the social dynamic in a particular context? The algorithmic level can be thought of as the cognitive algorithm, although it doesn't have to be a cognitive algorithm. It can be a psychosocial dynamic algorithm. But this is a really kind of a descriptive, low-dimensional system, but a formal process that describes how a particular behavioral goal is achieved. And in our case, the underlying implementation system is fundamentally the neural substrate, so the brain. Now, Van Rij and Baggio argue that we need to build a theory of capacities fundamentally at the computational level, particularly for psychological theories. That is our goal. And that if you build your theories of capacities at the psychological level, it constrains the way you look at the scope of algorithms or the range of algorithms that you use to understand your behavior and the ways that that can be implemented. So they're going to argue, and we're going to hold to that in this class, that fundamentally you should be looking at the computational goals. Now, why is that relevant for a class in data science? Because a lot of the data that we collect in our fields is fundamentally just behavioral output or responses of a particular set of neural systems. That is the level at which we get data. So framing our theories helps because it helps to frame the way we think about doing the analysis of the data we collect. So how do we build a theory, which we'll call F, of capacities, C? Van Rij and Baggio argue that we should use the process of abduction, formal abduction, which is simply reasoning from observations to generate possible explanations. It's generating hypotheses. Abduction itself has two sub-processes, redundantly named so abduction proper, which is just simply the process of generating candidate hypotheses, which in turn involves the step of selecting the best explanatory hypothesis. So of this set of possible hypotheses, using inference to choose the best explanation. And then you use this inference to best explanation, which happens from looking at data and observations, to refine, again, the set of possible hypotheses that you generate. It's this constant dynamic between generating hypotheses from a high-level theory of capacities, using inference to choose a best hypothesis, and using that best hypothesis to go back and generate a new set of more constrained hypotheses. Now, this process is going to be highly sensitive to prior knowledge. So how you frame your theory will determine the shape or form of your hypotheses. And since that will determine the initial conditions by which you start your search, that will essentially constrain your entire approach to looking at observations to either validate or invalidate your fundamental theory. So, what should a theory look like? The authors propose that this form represents the structural form of a theory. So for any set of capacities C, they're generated from a function that takes in a specific set of inputs and generates a specific set of outputs. The function f, given an input I, produces an output O. And that process defines the capacities of the system. We're going to come back to this quite a lot. This F given an input equals an output. You'll notice as this class progresses becomes the fundamental form of a statistical theory as well. So hold on to this. Now, this theory can be made with words or formal logic. We're going to really focus on how this can be produced in equation forms because those are going to be most closely relevant to the way that we test our theory with observed data. So this can take the form of a simple linear regression where you just have two inputs, I1 and I2, who are weighted by two regression coefficients, beta 1 and beta 2, with some noise. This can take more complex forms. So instead of a simple regression, this can be a nonlinear equation where you have the output be determined by some squared input and a functional change on another input plus noise. The fundamental form of F, that theory, can be as complex or simple as you want. But the form of these relations from input to output, specified by some transformation function, is essentially the fundamental form of any theory. So when you're thinking about a theory in your field, whether it's cognitive development, whether it's social psychology, whether it's cognitive psychology, whether it's neuroscience, systems neuroscience, or cellular neuroscience, ask yourself, what are the capacities? What are the inputs? What are the outputs? And what's changing those outputs? And if you frame your theories in that way, it frames the theory in a way that makes it experimentally testable. So the authors present an example of this in the context of foraging. So imagine that you're an animal and you are wandering an environment that has 4 food sites or a set of food sites, and you have to make the decision, or you're exhibiting the behavior of foraging to the different sites. So in the example I have on the right, I'm showing 4 sites, but this works for any number of sites. You can formalize the process of foraging, F, as being a system that takes a set of inputs, which in this case are a set of sites, where each site hosts a particular amount of food, and the distance between each pairs of sites defines a travel cost. So you have places where food is, you have distances and environmental constraints that make it more or less costly to go between them. So you can lay out that as your set of inputs. The output is an ordering of elements or visits to each site and the amount of food that you collect relative to the amount of energy it takes to collect them. So the process of foraging involves calculating these inputs of sites and distances and costs and producing a sequence of paths, if you will, that determine how you should forage in this environment. Functionally, you can present it as a set of equations like this, where your capacity for foraging takes the inputs S, which are the sites, and sums across all of those sites the amount of food that you would get over the cost it takes to visiting any pair of sites, plus the overall cost of the sites that you visit itself. So you can boil down the process of foraging as a function of this very simple evaluation. And once you have this structural form of a theory, the idea is, how do you construct it? How do you evolve it? And the authors propose this theory evolution, which we're going to come back to multiple times, whereby you develop a theory, you frame it, you test it, you use that evidence to change the theory, and you keep going with this cycle. So they view this cycle this way. In other lectures, I showed the Wallace wheel, which it basically says the same thing. Now, according to the authors, what you really want to do is start with an informal verbal theory to set your conceptual frame. They argue actually don't start with a quantitative theory yet, but set up a system of logic verbally that sets your conceptual frame. operationalize it to a formal structure to make hypotheses, the act of abduction. So once you have a verbal theory, make a very quantitative hypothesis with which you can test your theory. Design tests to evaluate the hypothesis, and use empirical results to refine the form of your theory. And do it all over again. Form a verbal theory, formalize it in a set of equations, maybe go back and forth on that for a while until you have something that's testable. Test it with a set of observations, whether or not that's just cross-sectional observations or experimental data. Take the results, reconsider it in the frame of your formal theory, use those results to change your verbal theory, which changes the functional form of your theory, which generates new hypotheses which you can test, and keep doing this. And the idea is that this cycle never really ends. We're just constantly framing and forming these theories in a very specific quantitative sense. Now, the main goal of empirical research, including experimentation and computer simulations, is to narrow the space of possible functions after relevant theoretical constraints have been applied. So what you need is a way of constantly reducing the space of possible forms of your theory through that theoretical cycle and a set of theoretical constraints. So for example, you might have 3 theoretical constraints. Let's say tractability, evolvability, learnability. Could be constraint 1, 2, and 3. All of those together, where they all converge, define the real-world capacities of the system you're trying to test. And what that does is that narrows the space of possible forms of your theory and gives you kind of a narrow testable range of possible shapes with which your theory of capacities can take. And according to Van Rijn and Baggio, this is the fundamental way by which you try to constrain the shape of the theory that you develop. But that all depends on following that fundamental form, following that functional form of your theory. For this class, we're always going to follow that functional form because it relates directly to the ways that we analyze our data using data science tools. Now, I'd like to shift gears for a little bit, now that we've defined the shape or form of our theory, to exploring how you can formulate a good theory. And by good, I mean good from a data science perspective, where you can evaluate it effectively using data analytic tools. So we're going to shift gears to the Guest and Martin paper. Guest and Martin proposed the idea of open theorizing, which is providing a transparent genealogy for where predictions, explanations, and ideas for experiments come from as a means of developing theory. So building off of that theory cycle that we just talked about, how do you create essentially a genealogy of evolution of your theory? And they argue that this needs to happen out in the open. Normally this happens, or historically so, this happens quietly in a lab by individual researchers as they kind of do their work and we see the final output. But they argue that we need a process by which this is specified and tracked in order to show how a theory moves, how a theory evolves over time. So this explicitly states or formalizes the theoretical cycle that Van Rijn and Baggio proposed. And the idea is you start with some form of your theory following the constraints that we just discussed. You do some evidentiary tests that gives you an output. You refine your theory again. You come up with theory 1.1. This more specific theory then makes a new hypothesis that you test. The outputs of those two tests further revise your theory. You get more evidence, and maybe that forces you to fundamentally revise the shape or form of your theory. So you come up with theory 2.0. And then you do it again, and this process keeps going until you either run out of possible ways that the theory can evolve, or you have to discard the theory altogether. Guest and Martin argue that making this process open and transparent in both communicating how it is done and the means by which it is formalized and communicated are important for understanding and where theories come from, how they originate, and what their constraints are. Now, Guest and Martin argue that in psychological sciences, and I'm going to include the neurosciences in here too, we need to do this by making our theories formally computational, using computational modeling as a way of presenting our theories. Computational models follow all of those constraints that were proposed by Van Rhee and Baggio. Now, in order to avoid confusion in terms, because we talked about the computational level of analysis from Marr, what I'm going to do is refer to this as a quantitative model instead. A quantitative model is just the process by which relations are described using a formal logic, for example mathematics, that removes ambiguity and constrains the dimensions of a theory. Basically, it moves from colloquial, verbal descriptions to formal theories. The benefits of adopting a computational or quantitative modeling approach for your theory is that it automatically conforms to open theorizing. The form and constraints of your theory are explicitly described each time you generate them. And it makes the projection from theory to hypothesis to predictions easier. So, adopting a more quantitative way of defining your theories and your hypotheses makes it easier to test them because they're already in the form that you're going to test using quantitative data. Now, in order to illustrate why adopting a quantitative theory is beneficial, Guest and Martin use a toy example. Let's say that your favorite pizzeria has a special, 2 12-inch pies for the price of 1 8-inch pie. Is this a good deal? Now, an informal theory, a colloquial verbal theory, usually goes through this kind of a logic. Well, 2 pies are twice as much as 1 pie, and 18 inches is only 50% more than 12 inches. So given that we have 100% more pie versus an 18-inch, it's going to be a better deal. And so the answer is yes. You think that this is a good deal to take the 2 12-inch pies. Now, the nice thing about this example is you can actually easily put this in the form of a quantitative theory. So instead of just using the colloquial verbal 2 pies is twice as much as 1 pie and 12 inches is only 50% more than 18 inches, well, why don't we just quantify the amount of food? We know that the area of food is just pi r squared because the pies are circular. So we can quantify the amount of food you get in each option by just summing over the number of pies by the radius of the pie, which gives us the surface area. And then we can come up with a formal decision term, right? We can say whichever option has the most surface area, the most food, is the better deal, because they're both the same price. Now let's see how this plays out. We'll just use that exact example. 2 12-inch pies has a food surface area of 226 square inches. 1 18-inch pie has a surface area of 254 square inches. So the answer is no. This is not a good deal. The difference between the quantitative theory and the informal theory is that the quantitative theory specified specifically an operationalized definition of what the value and quantity of food is, and specified a decision criterion for how to make your selection. The informal theory relied on heuristics. And as you can see, those heuristics in this case led to the wrong or incorrect decision. Now this is just making the argument for quantitative theory. Guest and Martin go further and say the value of making this a computational theory is that you can easily implement this theory in a formal system like Python or R. So they present a Python example where you can take this formal quantitative theory and put it into a very simple set of Python. This is 5 lines of Python code, 6 lines of Python code. And now you have a way of sharing this theory with other people. You can share this Python code with other people, and people already have access to your theoretical model, which is harder to do if you rely on the informal, more verbal-based theories. Guest and Martin then say, we need to rethink the path by which a theoretical cycle is implemented. So this is an expansion off of the theory cycle proposed by Van Rhee and Baggio. And they say we need to kind of think of all levels at which you can specify and form your theory and test it. So starting at the top, you need to start with a framework. This is just a conceptual system and building blocks, a context of formalism. Connectionism, working memory, ACT-R or symbolic systems. That sets essentially a frame by which you construct a computational version of your theory or hypothesis. Within that framework, you develop a scientific proposition that describes causal relations. A function of inputs produces outputs. From that theory, you develop a specification. This is a formal or formalizable description of the system to be implemented based on the theory that you have. Based on that functional form of inputs and outputs, specify or operationalize essentially what you're going to test. Are you going to use natural language processing? Are you developing a mathematical specification of your hypothesis and theory? Within that, you have a particular way of instantiating that computational model. And this you could think of as the code. In this class, we're using R, but you can use MATLAB, Python, C. But this is the formal implementation of the specification. So this is going from the geometrical equations of pizza surface area to the Python code. That allows for you to now develop a narrow testable statement involving measurable terms, a hypothesis. These are your specific operationalized constraints of your specified theory. So now when we talk about a hypothesis, we're talking about a specific model that can be specifically implemented in a framework, in an implementation system like Python or R. Using that narrow testable statement, you can collect observations from the real world and test it. And then you have this path function that works your way back up. So your data constrains your next set of hypotheses, or you evaluate your data in the context of your hypothesis, which revises upward the specification and the theory, which sometimes maybe even puts a change in your framework. And then you start all over again. The systems highlighted in the pink background, theory, specification, and implementation, these are typically areas that are just compressed or altogether ignored in a lot of psychological research. And so the authors are highlighting it as a way of saying we need to think carefully about the specific proposition that we're making, the formalizable description of it, and how it's implemented. Often we just start with hypothesis and data with some vague theoretical wrapping on top. But these are important, particularly if we're going to argue that you need a formal quantitative description of your theory and hypothesis before you go out into the world and test it. Constructing the hypothesis is one of the hardest things that you will do in data science. And it most tightly links to the statistics that you use in your research. So the overall take-home message from this lecture should be that having a formalized theory, preferably in quantitative terms, makes it easier to communicate and test your ideas. And theory and evidence dance together. Theory defines where and how you look. Evidence revises that search. Think of the process of research of not just putting together a theory and a hypothesis, throwing it out to the world to test it, and then either accepting or rejecting it. It's a constantly evolving process that relies on a very specific framing and form that can be tested in very specific ways with data analytic tools. And these work together to define your search and to define the evolution of your theory. It doesn't start and stop with one experiment. It's a set of experiments, a set of tests that evolve over time.